Hello everyone. Welcome to the 10th part of Modeling, Analysis and Design of PEB structure. I am Surajit Ghosh, and in this session, I will discuss about different types of gravity load including dead and live load and how to apply these loads correctly using group. I will use the same PEB structure with tapered column and rafter with proper beta angle, member offset and tension only specification. You can check the complete playlist to get an overview of this model. In last part, we have created different primary load case, and I will use the dead and live load case to add the load items. Before that, I want to discuss what are the structural and non-structural gravity loads that we need to consider for analysis and how to calculate the load intensity. Let's start with the dead load, which is nothing but the weight of structural and non-structural element. All these member, like this large span rafter with variable depth, has significant weight which is carried by the supporting member. During analysis, we can consider the weight using self-weight command. For any gravity load, applied load is in downward direction. So direction is y with factor -1. For self-weight command, program calculates the load per unit length using density of the material and section dimension and apply the load on each member as UDL. We need to assign this self-weight command to all the members present in this model. With this, we have considered the dead load of all structural components. Apart from this, there are several non-structural elements with significant weight. For example, the roof panels. In any PEB structure, normally galvanized steel or polycarbonate corrugated sheets are used as roofing element. As the thickness is small with higher flexibility, it behaves more like a flexible diaphragm with both in-plane and out-of-plane deformation. That's why we need to model this using finite element mesh. But if we model the roof, it increases the modeling and analysis time. For any second order or iterative analysis like section selection, finite element roof is not efficient. So we normally skip modeling the roof and apply the dead load directly on the supporting members which carry and transfer the load, like purlin and rafter. I have already discussed this in part 1.1. You can check that for more details. For roof panel, unit weight or area load depends on the material of the sheet and thickness. In general, load intensity varies from 0.12 to 0.18 kN per meter square. We need to confirm this from the technical specification of roof panel. Along with this, there are several additional elements which we need to consider during load calculation. For example, light fitting, duct or pipe supporting structure, insulation or architectural component which are connected with the rafter or purlin. Also, there are few other attachments like the turbo ventilator or ridge ventilator. All these contribute to gravity load which is finally carried by the purlin and rafter and transferred to the column. As the load intensity is small, we can consider this combinedly with the roof panel weight. Total load intensity varies in between 0.05 to 0.3 kN per meter square. For this model, we will consider the additional load intensity as 0.1 kN per meter square. Apart from this, if there is any additional attachment, that should be considered separately. For example, if there is any solar panel connected on top of the roof or an antenna, we need to manually calculate the weight of these components and apply the load directly on the roof or add this with the roof load. For this model, there is no such attachment and the total load intensity is 0.25 kN per meter square, 0.15 for unit weight of sheet and 0.1 for the additional non-structural elements. How to apply this load on an inclined roof? We can use the floor load command. Load intensity is 0.25 kN per meter square in the downward y direction. For more accurate analysis, we can switch on this one-way option and distribute the load only on the purlin. Finally, specify the range to auto-identify the closed panel. But there is one problem. During panel identification using range, STAAD is unable to identify the floor correctly if it is not parallel to any global plane or inclined. Range option is applicable when the floor is parallel to global plane. Let's apply the load on the left side of the roof using range and see what happens. We can select the node cursor to check the level. The lowest Y level is 8.5 meter and highest is 10.7. X range is 0 to 12.5 meter and Z range is 0 to 54 meter. We can specify these values as range of the floor and add the load. See, though the load item is added, program is unable to generate the load as no panel is identified due to slope. For such slope group, floor range will not work and we need to use some other option. In last couple of sessions, we have generated few member group and floor group, one for the left side of the roof and one for the right side, with all rafter and purlin member which carry and transfer the roof load. Now we will use this group for load assignment. You can check part 2.5 and 2.6 to get an idea how these groups are generated. In the floor load window, there is an option available to apply the load on a group. As you can notice, these floor groups are already listed here. Note that only a group with type floor can be used for floor load application. Group with other type like member or geometry group cannot be used for floor load. We can select the roof left group instead of range. There is another important option available for group: inclined floor. If the floor panel is not parallel to any global plane, then this option must be selected to apply the load correctly on that inclined panel. Else, floor load will not be generated properly. As range is not suitable to apply load on an inclined panel, this option is available only for floor group. With this change, we can notice that the load is applied correctly on left side of the roof. For other half of the roof, we can create another floor load with same load intensity and use roof right group to apply the load on the right side of the roof. All members which are included in the floor group is used for floor load distribution. For an inclined roof, I always recommend creating a floor group first with all the members which carry and transfer the load, and then use that group to apply the load. We don't have to specify any range or level. Also, we can apply load on part of the roof. If there is any area with additional load like few solar panels or transparent sheet with separate unit weight, we can create a new floor group and use that to apply floor load on that portion. There is another load which we need to consider: dust load. In last video, I have discussed about different types of load required for analysis and design. Also the design codes which we need to follow to calculate the load intensity and distribution. Any structure which is located in a dry and dusty area or within a plant, dust is accumulated on the roof and exposed surface, and we must consider this load for analysis. IS 875 Part 2 and SC 7 can be followed to calculate the load intensity. Normally 0.5 kN per meter square load is considered as dust load. We can create a new primary load case with load type dust and add the dust load under this. But there is one problem with this approach. For IS 800 or SC 7 autoload combination factor for dust load is not available. If we use these codes to generate load combination, this load case will not be considered, and we need to modify the load combination rule to include dust load. What I prefer, add the dust load under dead load case as the combination factor is same. But if the combination factor is different from dead load, then it is better to create a separate load case and modify the combination rule. I will discuss this later. For now, we'll use dead load case, add a new floor load with intensity -0.5 and apply this to the same floor group on left and right side of the roof. With this, gravity load application on the roof is now complete. Next, we need to consider dead load of the side panel. Normally side panels are connected to the girth, and it is better to apply the load directly on this member as UDL rather than area load involving column. To calculate the load intensity, height of the panel is required, which we can check using node-to-node cursor. Total height is 8.5 meter. There is a 3 feet brick wall with an overlap. Roughly the height of the panel is 8 meter. So total load intensity is 0.15 into 8 or 1.2 kN per meter, and it is carried by two equally spaced girth. UDL intensity on each member is 0.6 kN per meter. We need to add dust load and sag rod weight with this. I will ignore that at this moment. We have created a member group with the girth member, right? We can use that group to apply the member load by selecting all these members. Then create a member load with intensity -0.6 in the global y direction and add. Finally, we can assign this load to the selected members. It's really easy to work with different types of group. That's why I have generated these groups. And not only for load application, I will use this group later for design parameter assignment. We are done with dead load. Depending on the structure type and usage, there might be few other components which can contribute, like gantry girder and crane load, load from any machine or plant unit. If the machine is placed directly on the floor, then it is not required to consider the dead load for frame analysis as the load is transferred to the support. But if it is placed on an elevated platform which is connected to the main frame, then we need to consider the dead load and dynamic components. That is a different topic. We can discuss this in future. Finally, we need to apply live load only on the roof. There is no elevated floor. Also, live load on the base is not required for frame analysis. We can use IS 875 Part 2 or SC7 to calculate the load intensity. In Table 2 of IS 875 Part 2, live load intensity for different types of roof is provided. For this structure, slope of the roof is exactly 10 degree and it is inaccessible with only maintenance access. So the live load intensity is 0.75 kN per meter square. If the slope is more than 10 degree, then live load is proportionately reduced. We can apply this load as a floor load with intensity -0.75, and once again we can use the same floor group. I think it is clear now how this floor group minimizes the modeling time and effort. We need to assign same floor load on both sides of the roof, and with this, our gravity load assignment is complete. Depending on the structure type and usage, there might be some other gravity load like snow load. I have already discussed this in the last part. This dead and live load case, not only used for gravity analysis, we'll use these loads later for seismic weight or mass model generation using mass model generator with proper load factor. That's all for today. I hope you have enjoyed this series on PEB structure. Thanks for watching.